Okay, and part of these substitution reactions, you have to memorize the 4 different ways by which we are doing our arrow pushing. So we have looked at the acid-base reactions where we did the protonation and the deprotonations. Then we looked at the nucleophilic attacks with a negatively charged nucleophile, and when you had a neutral nucleophile. And that neutral nucleophile has to be a protic molecule. Protic just indicates that it should be able to make hydrogen bonds or the hydrogen next to the electronegative element, which can be given away during the deprotonation part. So whenever you will have a neutral nucleophile, you will get a charged intermediate. We cannot just use this charge intermediate for our further reactions. We have to make sure that we reduce or deprotonate this hydrogen to a neutral molecule. The third kind of mechanistic steps that we looked at were the loss of leaving groups. Leaving groups have to be weak base. So when they leave, when you look at the chemically balanced equation, your leaving group should be a weak base. Leaving groups can leave on their own. Leaving groups can be kicked out when an incoming nucleophile attacks. Usually, this nucleophile would be a negatively charged nucleophile. And the fourth kind of mechanistic arrows that we have seen are the rearrangements. And when we were looking at rearrangements, we also looked at carbocations, how they are classified and how they are very electron deficient. And one of the important properties of all carbocations are that they look around to rearrange. Whenever you will have a carbocation, it will rearrange. Rearrange to what? To a more stable carbocation form. Okay, so just remember there is a difference between resonance structures and rearrangements. Rearrangements can be 1,2 hydride shifts, or rearrangements can also be in the form of 1,2 alkyl shifts. The smaller the alkyl, the first one it would be to move. And all of these loss of leaving groups are for all our ionic reactions, that is, are heterolytic cleavages. Ions are formed by heterolytic cleavage. So that is an important part of this particular chapter. After this, we had started looking at the nucleophilic substitution reaction, where we started to look at the SN2 kind of a substitution. And in substitution of the bimolecular order, the SN2 order, we realized these few things. Okay, the nucleophile needs to be a strong nucleophile. What does a strong nucleophile mean? Will a neutral nucleophile work? No. Only negatively charged atoms would work as nucleophiles for SN2 reaction. You need non-bulky substrate. Why the non-bulky substrate? So that this 5-membered transition state does not feel crowded. Okay? And so tertiary alkyl halides, or where X is the leaving group on the tertiary carbon, will not do SN2. Secondary can do SN2, but better than secondary, it is the primary alkyl with a leaving group that will do the SN2 better. Yeah. So based on our transition state, we have figured out we need a strong nucleophile which can kick out the leaving group. We need a less hindered site which can be accommodated in this crowded space. The reaction mechanism is overall concerted. It occurs right after each other. So the bonds are breaking at the same time. When the nucleophile is attacking, the leaving group is leaving, and in between this very, very, very short-lived transition state is appearing. Another factor that we have to look at is the solvents, and we have looked at protic solvents. Just like protic molecules, protic solvents also give away protons. But SN2 does not want a proton, because if there are protons, they will slow down your nucleophile, which is not acceptable to SN2. And so after your acid-base reactions, SN2 reactions are the competing reactions. So most of the times, whenever you start to look at a chemical reaction, if I give you A plus B, always think, can an acid base occur? If not, can a substitution occur? If a substitution can occur, look out for SN2 first. Why? Because SN2 reactions are concerted and fast. They will occur at a faster rate than other form of substitution, which we are going to look in a few minutes. All right, so let's look at some examples that we had started looking at on Friday. And also, please remember, if a solvent is not given to you, just assume that it is a preferable solvent for that substitution. And the room temperature, if no temperature is given to you during the reaction conditions, assume it is the room temperature. So we had started to look at these examples right here. We had looked at this primary substrate. We had decided the leaving group was good. What about the nucleophile? It is negatively charged, and hence it is going to be a good, strong nucleophile. No solvent is given, no temperature is given. All of these are pointing a favorable SN2 mechanism. And so what is the favorable mechanism? The electron rich attacks the electron poor. That is your first step. Carbon will have to keep its octet. So the fifth bond with this leaving group will go. Is this a good leaving group? Yes, all mesylic sulfonates. So this is just a form of sulfonate. And as you can see, if it forms, it will be very, very stable. It will be a weak conjugate base, so a weak base because of its resonance and induction stabilization. But this is the main organic molecule that we are interested in. So when I ask you to write products, you don't have to write this byproduct. This is the product that you must be focusing on. What if you had the same nucleophile, but now same leaving group, but now instead your substrate is a secondary substrate? The reaction will still occur. The nucleophile will attack the electrophilic carbon, and the leaving group will leave. The same attack will occur. The same product, similar product will form. A similar substitution product will form. Secondary substrate favors SN2. Leaving group, great. Nucleophile, strong. Solvent and temperature are not given, so you will assume that it is favoring your SN2 mechanism Still, they are favoring this SN2 mechanism. So this reaction will occur and this reaction will also occur. However, out of A and B, which is going to be a faster reaction? It will be reaction A. And why? Because your substrate is less bulky here. Your transition state will form faster in this case, and hence your product will form faster in this case overall. Any questions? Any questions of why this will be faster? So these are the kind of questions that you can expect in your drill test and in your exam also. So if you don't understand them now, make sure that you ask me as we go. Between these two now, let's see, I have same substrate, same leaving group, but instead I have now changed my nucleophile. Instead of having the O negative, my nucleophile is C negative. And look at the reagent that I'm using. This is known as the Grignard's reagent. We will be using this again and again for the next few modules. So make sure that you are familiar with this. C negative compared to a O negative will be a better electron donor. So this is a stronger nucleophile as compared to this resonance stabilized molecule. Now, this resonance stabilized molecule can still be an electron donor, but not as strong donor as is this nucleophile. And so because this nucleophile is stronger, this reaction will occur faster than A and definitely faster than B. So if I ask you, out of all these three, arrange them in the fastest to slowest order or slowest to fastest order, we should now be able to compare those. What mechanism is this? Still SN2. Yeah, so looking at this, I had asked all of you to draw these out on your papers on Friday. Did you get a chance to do that? Can anybody tell me what will be the answer to this first equation? First of all, look at the substrate. Then look at the leaving group. Then look at the nucleophile, strong or weak or neutral. And then look at the solvent or temperature conditions. Taylor, are you here?
Yes.
Okay, can you help me with this? So what kind of a substrate do I have, Taylor?
I'm not sure.
Okay, so on this molecule, how many carbons are there?
3.
Very good. And on these 3 carbons, where do you see some polarity or some vulnerability?
The third carbon with the chloride.
Exactly. And so if you look at this particular bond, there is a polarity right here, making this carbon special as compared to the rest of the carbons. So on a molecule, you should be able to identify your electrophilic carbon. So Taylor, do you remember what is electrophilic? It is electron deficient, right? So why is this carbon electron deficient, Taylor?
Because the polarity of the chloride.
Exactly, very good. So the chlorine is electronegative and it is pulling the electrons from this carbon, making this carbon partially positive or electron deficient. So this carbon, how will you classify this carbon, Taylor? Is it primary, secondary, or tertiary?
Primary.
Very good. because this carbon is attached to only one other carbon, we will label this as a primary alkyl halide. Now, X can be any leaving group. Chlorine, bromine, iodine, OMS, OTF, OTS. So these are also great leaving groups, and your halogens, except for fluorine, are very good leaving groups. So this is a primary alkyl halide. The substrate is primary alkyl halide. What is the leaving group here, Tila?
The chloride.
The chlorine. And is it a good leaving group?
Yes.
Yes, very good. So we have these two under our information. What about sodium hydroxide, Tila? Is it a strong nucleophile, or a neutral, weak nucleophile?
A strong.
Very good. And where does the strength of this nucleophile come? Which atom is responsible for the strength of the nucleophile?
The oxygen.
Very good, because sodium is positive, oxygen is negative. Very good. Now, all the requirements for a SN2 mechanism are being fulfilled. So remember, it does not like crowding. It wants a strong nucleophile, and it wants a good leaving group, and it wants polar aprotic solvents. Since we are not given any of that information, we don't have to worry about it. So this oxygen is going to do the SN2 mechanism. Nucleophile attacks the electrophilic carbon, leaving group leaves. I'm going to draw out this structure up till this carbon. And what I'm going to do now here, Taylor?
You would add the OH.
OH, very good. And remember, there were two hydrogens here, which we did not draw, but they will still be there. Okay, very good, Taylor. Thank you so much. Does everybody understand how we did this? Anybody has any questions? Right, that's wonderful. Thank you, Taylor, again. So Elizabeth Chapman, are you here? Okay, I'll assume that you don't want to answer. Portia, are you here? Would you like to answer this question, Portia? I'm cold calling in. Everybody's cold calling me. Oh, Portia, you can't answer with unmuting? By unmuting yourself, I mean. Okay, so Portia, if you look at this is still a Cl, okay? What kind of a substrate do I have here? Oh, I see. So Portia, can you guess what is the substrate here? What kind of a substrate is here? If you're not sure, that's fine as well. We can work on that. Okay. So if you're looking at all these structures, how many carbons do you have here, Portia? How many carbons do you have here? 4, very good. So on all of these 4 carbons, do you see anything different, or any polarity, any vulnerability, any place you can add anything? So if you look at all these 4 carbons, this is the carbon where you have some polarity. And so this will become your electrophilic carbon. This carbon is attached to 2 other carbons. So this is a secondary carbon, and the leaving group of this carbon is on the secondary carbon, making this a secondary alkyl substrate. Any questions from anyone? This leaving group, sodium iodide, just like your other groups, iodide is going to be your nucleophilic part, the negatively nucleophilic part. This is a secondary substrate. The nucleophile is strong, the leaving group is good, the substrate is not bulky. All of these are pointing to which mechanism? The SN2 mechanism. And so your iodide is going to attack the electrophilic carbon, the electron deficient carbon, kicking out your leaving group. And so you will make the same structure here, but instead of chlorine, you will now have an iodine. Now this chlorine had a wedge kind of a bond. When you do SN2, and if you remember our intermediate that we have been looking at, what kind of attack does the incoming nucleophile does? It does a backside attack. Okay, so it's a backside attack where the hindrance from the leaving group is less. So there is an inversion of stereochemistry at the alpha carbon. What is alpha carbon? We'll look at that also. So this carbon, the inversion will happen and the new substituted group will be placed here. So this particular carbon at which the attack is occurring, to which the polar group is attached, is known as the alpha carbon. And why alpha? Let's look at a long chain of carbon. And let's say that this is where your group is attached. Okay, out of 1, 2, 3, 4, 5, 6 carbons, the second carbon has the functional group on it. The carbon with the functional group on it is labeled as the alpha carbon. That is the first carbon on the functional group. If you have a group like this, a carbonyl carbon, now where is your alpha carbon? This is your functional group, and the carbon next or on which your functional groups are attached, they are known as your alpha carbon. So this is just the numbering or the counting that we have seen. Alpha, beta, gamma, delta. To this alpha, there are 2 beta carbons attached. Since both of them are different groups, I can label one of them as beta, the other as beta prime also. Any question on this numbering? Similarly here, this carbon, which is part of the functional group, is not counted as alpha. The carbon next to it on which the functional group is placed is the alpha carbon. So in this carbon will be your beta carbon. So alpha carbon is on which the functional group is placed upon. So SN2 mechanism is being followed. So you will have inversion of stereochemistry, or the stereochemical inversion will be observed here. How the groups are placed in the space, in the 3D space, is what stereochemistry is. in this molecule, in this particular molecule, I have exactly same secondary Rx. Why? 1, 2, 3, 4, 4 carbons. On the second carbon, I have a leaving group, a great leaving group for that matter of fact. So I have a great leaving group. I have an acceptable substrate. What is my nucleophile here? Just like others, metal ion will get the positive charge. The carbon next to it will get the negative charge. So electron rich attacks electron poor. Remember this carbon, this alpha carbon, because of the polarity becomes electron poor. So when the electron rich attacks this carbon, the leaving group leaves. What does it leave as? You don't have to worry about that. Since I have not shown you any stereochemistry, you don't have to show me any stereochemistry either. But when a stereochemistry is shown to you, you have to show the inversion of that part. Am I showing the side products? I don't have to worry about that. You are just going to worry about the organic product that is being formed. Any questions? All right. So knowing your alpha, beta, and gamma, let's move on to our next substitution pattern. So far for SN2, what have we seen? We need no bulk. We need strong nucleophiles. We need polar aprotic solvents. The leftover substitutions are performed by the SN1 mechanism. So this should be a G here. Nucleophiles can be generated by heterolytic bond breakage or with the metal ions. Just like when we were looking at SN2 and I showed you that you must know the intermediate for SN2 to know its mechanism. Similarly, for SN1, you must know the intermediate that is being formed. For SN2, both your nucleophile and your substrate are going to be important. But for SN1, only your substrate is going to be important. So this is a nucleophilic substitution of the first order. What is the first thing that we see here? We don't see the nucleophile. We just see the loss of leaving group. If you pay attention, compared from your SN2, where the nucleophile attacks first, right? So in here, the nucleophile is attacking first in SN1. Because your nucleophile is weak, it is the leaving group that will leave first. Just to help that weak nucleophile. Now, when I say weak nucleophile, I still mean that you will know that they are just neutral protic materials. Okay? Just remember that. So we have looked at this mechanism also when we looked at the neutral protic material or nucleophile attacking. And we have looked at this mechanism also in form of deprotonation. And so the first thing that you need to remember in a SN1 is that a carbocation will be generated by the loss of leaving group. So when the leaving group will leave, it will leave behind a vacancy here. This carbocation, what is the habit or the nature of carbocation? It will rearrange. If it can rearrange, it will rearrange. So the difference between SN1 and SN2 is primarily because of the substrate and because of the nucleophilic strength. Usually when you have a bulky tertiary substrate, it can work with a strong nucleophile because of SN1. One of the products that you can see with a tertiary substrate will be OH. SN1 kind of a mechanism can generate this substitution. Even though you have a strong nucleophile, but a bulky substrate. Remember, SN2 will not do bulky substrate. SN2 will only do less bulky substrates. So know the mechanism of your SN1. This is just repetition of what we have done. So first, the leaving group will leaves behind a carbocation. If a carbocation can rearrange, it will rearrange. Remember the hydride shift and the methyl shift. So once it has rearranged, the nucleophile will attack. Because it is a neutral nucleophile, you need to make sure that it has a protic H on it. And this protic H can be taken up by any other group. It could be a same compound, the same nucleophile, or it could be something that you introduce from outside. So the rest of the substitutions, when SN2 cannot occur, SN1 will occur. SN2 are concerted and faster mechanistically. SN1, on the other hand, take their own good time and are very slow. Why do you think these are slow? Reason one, because of the carbocation. Carbocation rearrangements need time to happen, right? If you have to rearrange, if you have to look around, you need time to shift. The second is weak nucleophiles. Most of the SN1 reactions will occur with weak nucleophiles, neutral and weak nucleophiles. So the nucleophiles which are weak will move slow. Right? So knowing your SN1 mechanism, just remember that these are slower reactions. What do they need? They need bulky substrate. So we had looked for SN2, it needs non-bulky substrates. It definitely needs good leaving groups. If the leaving groups are not good, they still need that. Same thing as SN2. If the leaving group is not good, the carbocation will not form. Unlike SN2, SN1 need or can work with weak nucleophiles. Okay, and unlike our SN2, which needs the polar aprotic solvents, these love protic solvents. They need protic solvents. Why do they need the protic solvent? So that the protic solvents protons can aggregate around this nucleophile and make it move even slower. Why? So it gives more chance for the carbocations to rearrange, to have all that functionality, all that time for the carbocations to rearrange. Because once these aggregate around the weaker nucleophile also, the nucleophile will attack. There is no doubt about that. But when does it attack? If you have a protic solvent, it will slow the movement of this nucleophile even further. So if you look at this very nucleophile that I have here, this nucleophile is the source of the nucleophile, right? The electron donor. And this nucleophile, this very nucleophile, because of its protic nature, can also act as our protic solvent. So this nucleophile is working in double shifts, you can say. It's working as a nucleophile also, and it is working as a solvent also. So these are like the double shift, double working, very hard working kind of nucleophiles, you can say. Any questions? Okay, so this is just a repetition of what we just saw. The leaving group leaves first, then the nucleophile attacks. Once the nucleophile has attacked, if it is neutral, you will be fine. But if it is not neutral, you will have to do the deprotonation step, and you must show that in your mechanism if you're asked during the drill test. Then once the carbocation intermediates are formed, they will be doing rearrangements. Any questions on how the rearrangements will occur or what will happen? So let's very quickly look at an example here. And I'm going to use the similar kind of a nucleophile. So what are the things that we have to look? We are going to look at the same things here. We are looking at the substrate, the leaving group, the nucleophile, the solvent, and the temperature and other reaction conditions to decide our mechanism. So looking at this, what is the substrate that I have here? This is definitely going to be my nucleophile. What about this substrate? What kind of a substrate do I have? Primary, secondary, tertiary, or methyl? What kind of a substrate is this? Anybody?
Secondary.
It is secondary. Very good, Sammy. And why is it a secondary substrate? On a secondary carbon, this carbon is attached to two other carbons. And so this carbon is a secondary carbon. The leaving group is on a secondary carbon. So this becomes a secondary substrate, right? What kind of a leaving group do I have? Do I have a good or a bad leaving group?
Good.
I have a good leaving group, yes. What about my nucleophile? Is it a strong nucleophile, the negatively charged nucleophile? No.
No, it's weak.
And it is a weak neutral nucleophile. And this is how I will decide that even though I have a secondary alkyl halide, and remember secondary alkyl halides can do SN2, but in presence of only strong nucleophiles. So when you have a weak nucleophile and a secondary substrate, your secondary substrate is not going to do a SN2. It is now going to do what mechanism?
SN1.
SN1. Any questions on why my mechanism is going to be SN1?
Can you re-explain that? Why it's a SN1, please?
Yes, yes. So do you understand how this, what kind of a substrate do I have here, Kiara?
Yeah, I understand where the two came from and all that, but I don't understand how it's a SN1.
Okay, so tell me, we are looking at this list. Can you see this list? I'm not sure. So I have looked at my substrate. I have looked at my leaving group. I'm now looking at my nucleophile. Between these two, are you able to recognize your nucleophile, Kara? Is that a difficulty? I mean, What is a nucleophile? It's just an electron donor. And I may or may not give you these lone pairs, but you do know that oxygen will be having these two lone pairs. And so among these two structures, this is going to be your nucleophilic area, right? In acid base, we used to mark, this is my basic site or the electron donor. This is my acidic site, but in this case, it is the electrophilic portion. Do you understand that part? That much, Kiara?
Yeah, that makes sense.
And so this is a nucleophile. But for SN2 to occur, what kind of a nucleophile do you want? Kiara? For SN2, do you need a strong nucleophile, all negatively charged atoms, or you can work with a weak nucleophile also?
Would it be weak?
No, SN2 always needs a strong nucleophile. So for example, if you look at all these examples that we did, negatively charged, negatively charged, negatively charged, negatively charged, negatively charged, negatively charged. See that, Kara?
Yeah.
So for SN2, you need a non-bulky substrate, a strong nucleophile, a great leaving group, and then polar aprotic solvent. Do you know what does aprotic mean, Kira?
Can
Aprotic,
you
which
refresh?
cannot give away. I'm sorry?
I said, can you refresh my memory?
Yes, yes, yes. So protic just means which can give away a proton. Aprotic will not be able to give away the proton. Do you see that now?
Yes.
So for example, HCl. If you dissociate it, will HCl give you a proton? Yes.
Yeah.
And so HCl is a protic solvent or a protic material. So usually when you look at a hydrogen, if it is next to a electronegative element, we say that this hydrogen will be a proton or will become a proton, and hence HCl can give away a proton, and hence it is a protic material or protic solvent or a protic compound. Kira, does that help?
Yes.
Okay, good. So for your SN2, you just need to memorize the requirements for SN2. If the requirements for SN2 are not being fulfilled, then you look at, then you say that it is going to be SN1.
Okay, thank you.
Okay, so let's look back at this. So let me keep this on my list. So my substrate is a secondary alkyl halide. My leaving group is good. It's bromide. So bromide is a good leaving group. My nucleophile, is it a strong nucleophile or a weak nucleophile? It is weak. And hence SN2 cannot occur. SN2 only needs strong nucleophile. So for this particular substitution, for this particular reaction, acid-base reactions cannot occur. I do see a basic site, but I do not see a acidic site. So the acid-base reaction will not occur. What can occur is a substitution. What kind of substitutions? I will first look at SN2. Non-bulky substrate, great leaving group, and I want a strong nucleophile, but there is not a strong nucleophile, so SN2 will not occur. Which substitution will now occur is SN1. Remember, all the leftover substitutions are SN1. Any questions on why did I choose this to be SN1? So what is the first step that I will do? And if possible, please go ahead and write it in your pages also. So you will also be able to do these mechanisms well. The first step, if you look on my slide, and I know I will be drawing on my paper. Are you all able to see my paper a little bit at least? So I'm going to kick out my leaving group. Similarly, I will kick out my leaving group. Did you all see how I did it on my paper? A yes, a no, we cannot see. I'm assuming all of you are able to see it. So this leaving group leaves. What do I form here? A carbocation. And so I'm going to draw my carbocation. Did you see my carbocation? What is a carbocation? Carbocation is the intermediate, a planar carbocation intermediate. What is the carbocation going to do? If it can do rearrangements, it will do the rearrangement. So this is the loss of leaving group mechanistic step. Can this carbocation do rearrangement? This is a secondary carbocation, and remember there's a hydrogen on it. There was a hydrogen on this to begin with also. So this hydrogen is here. This carbon is lacking electrons, so that is why we are putting a positive charge on it. So this is a secondary carbocation. It can either jump to this carbon or it can jump to this carbon, the carbons next to it. If it jumps, the positive charge goes to this carbon, what kind of a carbocation will you form? A primary kind. So from a secondary, this carbocation would not want to go to a primary location. But if it goes to this location, it will become a tertiary carbocation. So what is the group? So if you look, there are 3 methyl groups on this carbon. No hydrogen is possible, but a alkyl shift is possible. So I'm going to rearrange. This methyl stays on this carbon. So on this carbon, the methyl groups, 2 of these methyl groups stay. This is attached to the carbon which had the positive charge. But now has what? It has its hydrogen and the methyl group. And the rest of the molecule stays the same. Is this completely balanced? No, I did not put my positive charge here. So when I did a 1,2 alkyl shift, so this is my rearrangement, I have now received a tertiary carbocation, which is more stable than a secondary carbocation. Any questions? Remember, any time a carbocation will form, it will rearrange. If it can rearrange, it will rearrange. So this is your electrophile. What is the next step? The nucleophilic part attacks the electrophilic carbocation. So the nucleophilic attack will occur. What kind of a nucleophilic attack? So if you remember, we just saw at the beginning of this class also, when you have protic nucleophile attacking. So when you have a neutral protic molecule attacking, it can attack a electrophilic carbocation also. Exactly similar mechanism is being repeated. You just have to know where to where. In this example, I had a nitrogen, the lone pairs of the nitrogen attacking this electrophilic carbon. In this example, I will have the lone pairs of the oxygen attacking this carbon. So nucleophile attack. Once the nucleophile attacks, I'm going to redraw the structure completely again. And remember, this was a CH3. I'm going to redraw the structure completely. 3 to C, these two CH3s. Do I need to draw my hydrogen here? I don't have to draw, but just for the ease, I will. And what else is attached now? My oxygen is attached, my CH3 is attached, and my hydrogen, this hydrogen is attached. What is the charge on this oxygen? A plus. Exactly similar situation I had here. So this nitrogen attacked, the lone pairs of the nitrogen attacked this carbocation. This positive charge was created. And now because of deprotonation, where did this base come from? It could be anything. It could be the same material. It could be an additional base. You don't have to know what it is. You just have to show a B negative to tell us that a deprotonation will occur. So this is your acid-base deprotonation mechanism. Base attacks this acidic protic hydrogen, bond between hydrogen and atom breaks. You will get your neutral material. Exactly in the same format, base attacks. What is this base? You don't have to know. It could be the same, it could be something else. You don't have to know. A deprotonation will occur. Base attacks hydrogen. Hydrogen breaks bond with oxygen. So this is your deprotonation part. CH3, CH3, O, CH3, CH, CH3. So all of this, if you will draw mechanism, you will be able to figure out your product. But the question is, what will be the stereochemistry here? When we do SN2 reactions, we know that we are going to get an inversion of stereochemistry, right? That's what we have seen, that your wedges will become dashes and your dashes will become wedges if you have a SN2 reaction going on. We see the inversion of stereochemistry. What happens to your SN1? When you have a SN1, you get 50% of your material attacking this planar site. This is sp2 planar carbon. So this is like a flat carbon. Nucleophile can attack from here. Nucleophile can attack from here. So 50% times the attack is from here. 50% of the time the attack is from the other side. So we draw a wavy line here, or you can draw OCH3, CH, CH3, CH3 plus enantiomer. So a racemic mixture kind of a thing will form. Do you get an inversion? No. Do you get the retention? No. It is just plain formation of racemic mixtures. Okay, let's do one more example before we start doing our figuring out. So I'm going to draw a Haworth projection. So this is the Haworth projection. These three bonds are coming towards me. I'm going to draw a chlorine which is above this plane. So I have drawn a flat ring. Above the ring is the Cl, below the ring is the hydrogen. Above the ring is the H, below the ring is the CH3. And let's do this. And let's just look at the substitution reaction only. So you have to tell me, and I'm telling you that there is no acid-base reactions occurring here, okay? No acid-base reactions. We will only be looking at the substitution reaction. So which substitution is going to happen here? A SN1 or a SN2? Remember, whenever I ask you that there is going to be a substitution going to occur, you must first look for SN2. SN2 needs a less bulky substrate, good leaving group, strong nucleophile, which is a negatively charged nucleophile, polar aprotic solvents. That's what SN2 needs. But what do we have here? We have a good leaving group in the form of chlorine. So this is the carbon that will be involved in our substitutions. We have a good leaving group. We have a strong nucleophile. But what kind of a substrate do I have here? Anyone? Ariel Wallace, are you here? She's not here. Larian Clausel, are you here?
Yes.
Okay. Larian, can you help us figure out what kind of a substrate do I have here? Is it a primary, secondary, or tertiary, or methyl kind of a substrate? So what kind of a alkyl halide is this? It is attached to what kind of a carbon?
Secondary.
It is secondary, very good. But do you think there is a bulk attached or no bulk is attached? It is relatively bulky, right? Because of this ring, this substrate is getting bulkier. Does that make sense, Ariel? Okay, very good. And so with this bulky substrate, oh, actually, I'm sorry, this should be a CH3. So this is a tertiary alkyl substrate. But you are right, Larian, when I had that was a secondary substrate. With this bulky substrate, with this strong nucleophile, with this great leaving group, do you think a SN2 substitution can occur?
Yes.
So remember, for SN2, you cannot have bulk. Okay? And tertiary substrates, SN2 will never do tertiary substrate substitutions. Okay. So Larian, with this bulky substrate, which SN2 will not be able to accommodate in its 5-membered transition state. Do you think we can still do SN2? No. Right? Larian, is this clear to you or did I confuse you?
No, I think I'm fine now.
Okay, good. So with a tertiary substrate, even if you have a very strong nucleophile, it's not very strong, but it is a strong nucleophile because of the negative charge. Even with a bulky substrate and a nucleophile which is strong enough to have a negative charge, you cannot do SN2. If the substitution will occur, it will be SN1 type. Okay? And so this leaving group will leave. A tertiary substrate carbocation will form. The tertiary carbocation will get attacked by the nucleophile and we will see a racemic mixture. Oops, 1, 2, 3, 4, 5. So if you look here, the Cl was going up. So I'm going to draw one of our substituted groups going up. But 50%, the lower facing group will also form. So 50% this, 50% this. So these two will form in equal amounts. Why? Because once the carbocation forms, it will be a flat molecule. And this nucleophile can attack from the top or from the bottom. So if a substitution occurs, it will be via SN1. But in our module 8, we will see that substitution will not be the major mechanism for this. But for this module, up to this module, just remember, this is what you will be getting. Any questions? Now, I had this starting material. I'm going to draw similar starting material. This carbon had all the 3. And this carbon, instead of having a Br, now has a OH. And I have this CH3 OH. So my question to all of you is, between these two reactions, reaction A, where everything, the substrate is exactly the same, but the leaving group is bromine, and the nucleophile is weak methanol, I have exactly same substrate, but instead of bromine, I now have a OH. I have exactly same nucleophile also. So this is my second reaction. Salome, are you here?
Yes, ma'am.
Okay, very good. Salome, can you help us figure out? This was a SN1 mechanism. Why? Secondary substrate, but weak nucleophile. Great leaving group. What kind of a mechanism will follow here? Will I still have SN1 or it can be SN2 also?
SN2.
So remember, what do we need for SN2? Can you list out what is the kind of substrate we need for SN2? Go ahead. Methyl is faster than primary. then faster, then secondary. That's what SN2 needs. So the substrate is what kind? This substrate, what kind of a substrate is this, Salome?
Primary?
So looking at this carbon, how many carbons it is attached to?
2, so secondary.
So this is a secondary substrate, right? So secondary substrates can undergo SN2, yes. But let's not rush there. We have to look at all of our conditions. What kind of a nucleophile SN2 needs?
Strong.
Strong, negatively charged. What do you think is the nucleophile here?
Weak.
Weak, very good. So this is the first indication for you that SN2 will not occur here. You see that, Salome?
Yes.
And so we are going to see SN1. However, our conditions check are not complete yet. What about the leaving group here? We always need a good leaving group. What is the definition of a good leaving group? It has to be a weak conjugate base. What about the leaving group here, Salome? Do we have a good leaving group or a bad leaving group?
Good.
We have a bad leaving group. And so what do you think we can do? And so in the leaving group, when we were looking at the leaving groups, we had looked at these two examples. When you have a OH, which is a bad leaving group, you can convert it into a tosylate. Tosylate chloride with pyridine. HCl will be neutralized by pyridine and the rest of the O will be replaced by the MS. This is how you generate a great leaving group. You can have an MS, a tosylate, or a triflate, anything that you want. As long as you just list it as TSCl, TFCl, or just like I have, MSCl. There is another way with which you can convert your OH into a good leaving group. If you have a protic material present, this acid-base reaction will occur. The basic oxygen will grab the acidic hydrogen to become what? To become water molecule, which is your great leaving group. Water is a weak base. So you can either react your hydroxide with a tosylate chloride and pyridine, or use a protic solvent to convert your OH into H2O as a good leaving group. If you look at this example that I have here, what are the conditions that we have? Do we have the mesylate or the sulfonate kind of conditions? Or we can have a protic kind of conditions. Salome, which one do you think we have here? Do we have the mesylate chloride or we can use a protic solvent?
Mesylate chloride.
Okay, we can use it, but in our conditions here, we have this protic proton. So instead of doing a substitution reaction, the acid-base reaction will take precedence in this particular reaction. So we will follow SN1 eventually, but before that, an acid-base reaction will occur. Just like here, the basic oxygen grabs the acidic hydrogen. Similarly, the basic hydrogen will grab the acidic hydrogen from here. Okay, very good, Salome. Thank you so much. So I'm writing it out for all of you to see. This hydrogen will be abstracted out. This O will be right here. What is my acid-base product? The hydrogen, this hydrogen with a positive charge, plus CH3 with the O negative. And see, I have generated my good leaving group. So I cannot use OH directly. I will have to convert it either by using a sulfonate chloride or by using a protic material to convert into a water molecule as a good leaving group. Any questions so far? So between A and B, B will have to undergo extra additional reaction time. So between A and B, who will be faster? A will be a faster reaction. Why? Because OH is a bad leaving group. We had to take time to convert it into a good leaving group before we can do anything else with it. Now you have a leaving group. We will follow similar pathway. What is the first pathway? Leaving group leaves. Leaving group leaves. Leaving group leaves and makes a carbocation. So loss of leaving group, carbocation forms carbocation, rearranges. So you see this rearrangement occurring? Exactly same rearrangement will occur here also. One of the methyls will shift here. And remember, a carbocation will always rearrange if it can rearrange. Alkyl, shift, rearrangement. So this molecule and this molecule are exactly the same. I just wrote out these CH3s. Now I know the mechanism very well. It would be a great idea if you would also rewrite all of these mechanisms again and again. Whenever you solve for a problem, always write the mechanism. As much detail as possible. So now the nucleophile attacks. Nucleophile attacks. Deprotonation occurs where a base. What base? You don't have to know. Just write B negative. The base is going to abstract the hydrogen, do another acid-base reaction, and you will get your neutral product. Please see, both of these are exactly same products. This is my partially condensed kind of a structure. This is my bond line kind of a structure. Are you all able to see this similarity? But the only thing that was different was this OH. The OH took time. It took time to convert into a good leaving group. So protic materials will help make great leaving group, as we have discussed during the other leaving groups also. So looking at this structure, earlier we had this is also secondary RX, secondary substrate. This carbon, the leaving group is on a carbon which is attached to two other carbons. So this is a secondary carbon. This is a secondary leaving group. But now I have a reagent like this. Is this a strong leaving group or a weak, is it a strong nucleophile or a weak nucleophile? So remember, for your substrate, for a SN2 to occur, primary, methyl, and secondary can do SN2. Your leaving group needs to be good. Your nucleophile needs to be strong. And your solvent should be polar aprotic. It should not be able to give away protons. But if you look at it, yes, the substrate is secondary. So it is following SN2. It has a great leaving group, still following SN2. But look at the leaving group, the nucleophile. The nucleophile is not negatively charged. Your nucleophile is a weak nucleophile. And so this weak nucleophile and this great leaving group will still have SN1 because all the conditions for SN2 were not met. This reaction will be a SN1 kind of reaction. Okay. What will happen if we increase the concentration of this? But remember, the rate of SN1 reaction is only dependent upon the concentration of the substrate. So even if you increase the concentrations of your nucleophile, nothing will happen to rate. But what will happen if you change your substrate into a tertiary substrate? If you had a tertiary substrate, same nucleophile. Of course, because of the weak nucleophile, you will still have SN1. So both of these are SN1, this C and this D. But which is going to be faster? The one with tertiary substrate will be faster. Why? Because when the carbocation will form, it will already be a stable tertiary carbocation. You will not have to worry about that. Let's look at another last example that I wanted to show us. I wanted a tertiary substrate, a secondary substrate, and a primary substrate. And if I have CH3NH2, let's say that a SN1 occurs. Where will the SN1 occur? At the primary location, at the secondary location, or at the tertiary location? Which product will be the major product? Of course, the tertiary carbocation generating product will be your major product. So the substitution will occur at this location if you have a SN1 going on. Any questions? Everybody understands everything? That's a good thing. Let's try to do a quick lookout. what will be the mechanism for this particular reaction? Okay, and your choices are acid base. Of course, acid base is going to be the top choice all the time. SN1, SN2. Now remember, SN2 will be a topper choice, a better choice than SN1. So whenever you're looking at substitutions, always look for SN2 first. If the reaction conditions cannot fulfill the SN2 conditions, then you know that you're going to have a SN1. Or there will be no reaction. That could be a possibility as well. So for this particular reaction, and go ahead and write this down because I'm going to do a poll for you. So for this particular reaction, what is the first thing that is going to happen? The first mechanism. Okay, 10 more seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and I'm very, very happy with the results. And that is the right thing. The first mechanism that will occur here is the acid-base reaction. And if you look back here, the acidic hydrogen and the basic oxygen, the lone pairs from here are going to attack or abstract out this hydrogen. You are going to get compound like this. And in this particular presence, you are now going to start having your SN1 mechanism. And so the first thing is definitely acid base. Leaving group leaves. What kind of a carbocation has been generated here? A secondary carbocation. Can this carbocation go anywhere else to become more stable? So rearrangement, is it possible? If it goes at this location, it is going to become a tertiary carbocation. But if it goes to this location, it will still be a secondary carbocation. Okay? So instead, it will go and jump here. But at this position, it has an additional advantage. So this hydride shift will occur. This hydride will go at this carbon. The positive charge will come here. What we have in our hand right now is a tertiary allylic kind of a carbocation, which is very, very stable. And this bromide from this location will do the nucleophilic attack. And so what do you see here? If you start counting 1, 2, 3, 4, your OH was on the 4th carbon, but 1, 2, 3, your incoming group is on the 3rd carbon. You have a arranged, and of course racemic material. Why racemic? Because if 50% of the bromine attacked from the front, 50% of the bromine would also attack from behind. So you will get a racemic mixture, 50-50 racemic mixture, which is rearranged product. Instead of getting it from your original 4th location, it is now at the 3rd location. So whenever you will have SN1 mechanisms, you will also see rearranged materials. So tomorrow we will start with our module 8. And I will also try to do some more examples before that so we can see the differences between SN1 and SN2. Okay.